Chapter 1. Force. Syllabus. A. Force, work, power, and energy. First, turning forces concept. Moment of a force, forces in equilibrium, center of gravity, discussions using simple examples and simple direct problems. Scope of syllabus. Elementary introduction of translational and rotational motions. Moment, that is turning effect of a force, also called torque, and its CGS and SI units. Common examples: door, steering wheel, bicycle pedal, etc. Clockwise and anti-clockwise moments. Conditions for a body to be in equilibrium, translational and rotational. Principle of moments and its verification using a meter rule suspended by two spring balances with slotted weights hanging from it. Simple numerical problems. Center of gravity, qualitative only, with examples of some regular bodies and irregular lamina. Second, uniform circular motion. Scope of syllabus. As an example of constant speed, though acceleration, force is present. Difference between centrifugal and centripetal force. In class 9th, we have read that a force, when applied on a rigid body, can cause only the motion in it, while when applied on a non-rigid body, can cause both the change in its size or shape and the motion in it. In mathematical form, force applied on a body is defined as the rate of change in its linear momentum. That is, F is equal to dP upon dt, which is equal to d of mv upon dt, or F bar is equal to ma bar. If mass m is constant, the force is a vector quantity and its SI unit is Newton, its symbol is N, or kilogram force, symbol is kgf, where 1 kgf is equal to gn, where g is the acceleration due to gravity, which is 9.8 meters per second. A. Moment of a force and equilibrium. Translational and rotational motions. A rigid body, when acted upon by a force, can have two kinds of motion. 1. Linear or translational motion, and 2. Rotational motion. 1. Linear or translational motion. When a force acts on a stationary rigid body which is free to move, the body starts moving in a straight path in the direction of force. This is called the linear or translational motion. For example, in figure, on pushing a ball lying on a floor, it begins to move. 2. Rotational motion. If the body is pivoted at a point and the force is applied on the body at a suitable point, it rotates the body about the axis passing through the pivoted point. This is the turning effect of the force, and the motion of body is called the rotational motion. For example, if a wheel is pivoted at its center and a force is applied tangentially on its rim, as shown in figure, the wheel rotates about its center. Similarly, when a force is applied normally on the handle of a door, the door begins to rotate about an axis passing through the hinges on which the door rests. Moment, that is, turning effect of a force or torque. Consider a body which is pivoted at a point O. If a force F is applied horizontally on the body with its line of action in the direction AP as shown in figure, the force is unable to produce linear motion of the body in its direction because the body is not free to move. But this force turns or rotates the body about the vertical axis passing through the point O in the direction shown by the arrow in figure. That is, the force rotates the body anti-clockwise. Factors affecting the turning of a body. On a body, the turning effect of a force depends on the following two factors. 1. The magnitude of the force applied, and 2. The perpendicular distance of line of action of the force from the axis of rotation or pivoted point. Indeed, the turning effect of the body depends on the product of both the above stated factors. This product is called the moment of force or torque. Thus, the body rotates due to the moment of force or torque about the pivoted point. In other words, the turning effect of the body about an axis is due to the moment of force or torque applied on the body. Measurement of moment of force or torque. The moment of a force or torque is equal to the product of the magnitude of the force and the perpendicular distance of the line of action of force from the axis of rotation. In figure, the line of action of force F is shown by the dotted line AP, and the perpendicular drawn from the pivoted point O on the line of action of force is OP. Therefore, moment of force about the axis passing through the point O is equal to force into perpendicular distance of force from the point O, which equals F into OP. Note, for producing maximum turning effect on a body by a given force, the force is applied on the body at a point for which the perpendicular distance of line of action of the force from the axis of rotation is maximum, so that the given force may provide the maximum torque to turn the body. Units of moment of force. Unit of moment of force is equal to unit of force into unit of distance. The SI unit of force is Newton, yes, and that of distance is meter. So the SI unit of moment of force is Newton into meter. This is abbreviated as Newton meter, Nm. The CGS unit of moment of force is dyne into centimeter. But if force is measured in gravitational unit, then the unit of moment of force in SI system is kgf into m, and in CGS system, the unit is gf into cm. These units are related as follows. 1 Newton meter is equal to 10 raised to 5 dyne into 10 raised to 2 centimeter, which equals 10 raised to 7 dyne centimeter. 1 kgf into meter is equal to 9.8 Newton meter, and 1 gf into centimeter is equal to 980 dyne centimeter. Clockwise and anti-clockwise moments. Conventionally, if the effect on the body is to turn it anti-clockwise, moment of force is called the anti-clockwise moment, and it is taken positive. While if the effect on the body is to turn it clockwise, the moment of force is called the clockwise moment, and it is taken negative. Remember this. The moment of force is a vector quantity. The direction of anti-clockwise moment is along the axis of rotation outwards, while of clockwise moment is along the axis of rotation inwards. On applying a force on a pivoted body, its direction of rotation depends on A, the point of application of the force, and B, the direction of force. Thus, the direction of rotation of a body can be changed by two ways. 1. By changing the point of application of force. Figure shows the anti-clockwise and clockwise moments produced in a disc pivoted at its center by changing the point of application of the force F from point A to point B. 2. By changing the direction of force. Figure shows the anti-clockwise and clockwise moments produced on a pivoted axle by changing the direction of force F at the free end of the axle. Common examples of moment of force. 1. To open or shut a door, we apply a force, push or pull, F, normal to the door, at its handle P, which is provided at the maximum distance from the hinges as shown in figure. We can notice that if we apply the force at a point Q near the hinge R, much greater force is required to open the door, and if the force is applied at the hinge R, we will not be able to open the door howsoever large the force may be. Because for the force at R, torque will be 0. Thus, the handle P is provided near the free end of the door so that a smaller force at a larger perpendicular distance from the hinges produces the moment of force required to open or shut the door. Did you understand that? Very good. Let's move ahead. 2. The upper circular stone of a hand flour grinder is provided with a handle near its rim, that is, at the maximum distance from the center, so that it can easily be rotated about the iron pivot at its center by applying a small force at the handle. Common examples of moment of force. 3. For turning a steering wheel, a force is applied tangentially on the rim of the wheel. The sense of rotation of wheel is changed by changing the point of application of force without changing the direction of force. In figure, when force F is applied at the point A of the wheel rotates anti-clockwise, while in figure, the wheel rotates clockwise when the force F in same direction is applied at the point B of the wheel. 4. In a bicycle, to turn the rear wheel anti-clockwise, a small force is applied on the foot pedal of a toothed wheel of size bigger than the rear wheel, so that the perpendicular distance of the point of application of force from the axle of wheel is large. The toothed wheel is joined to the rear wheel by a chain through their tooth. Examples of moment of force. 5. A spanner used to tighten or loosen a nut has a long handle to produce a large moment of force by a small force applied normally at the end of its handle, as shown in figure. The spanner is turned anti-clockwise to loosen the nut by applying the force in the direction shown in figure, while it is turned clockwise to tighten the nut by applying the force in a direction opposite to that shown in figure. 6. A jack screw used to lift a heavy load, such as a vehicle, has a long arm so that a less effort is needed to rotate it so as to raise or lower the jack. Conclusion. From the above examples, we conclude that the turning of a body about an axis depends not only on the magnitude of force, but it also depends on the perpendicular distance of the line of action of the applied force from the axis of rotation. Larger the perpendicular distance, less is the force needed to turn the body. Couple. A single force applied on a pivoted body alone does not cause rotation of the body. Actually, the rotation is always produced by a pair of forces. In the above examples, the rotation is due to the force externally applied and the force of reaction produced at the pivoted point. The force of reaction at the pivot is equal in magnitude, but opposite in direction to the applied force. The moment of the force of reaction about the pivot is zero because its distance from the axis of rotation is zero. So the force of reaction at the fixed point or pivot is not shown in figures. The pair of external force and the force of reaction is called a couple. Thus, two equal and opposite parallel forces not acting along the same line form a couple. A couple is always needed to produce a rotation. For example, when we open a door, the rotation of door is produced by a couple consisting of two forces. First, the force which we exert at the handle of the door, and second, an equal and opposite force of reaction at the hinge. Sometimes we require a larger turning effect when two forces, equal in magnitude and opposite in directions, are applied on the body explicitly such that both the forces turn the body in the same direction. Example, to open the nut of a car wheel, we apply equal forces, each F, at the two ends of the wrench's arm in opposite directions as shown in figure. Similarly, while turning a water tap, tightening the cap of an ink pot, turning the key in the hole of a lock, winding a clock or a watch with the key, turning the steering of a car, driving the pedals of a bicycle, etc., a pair of forces, that is couple, is applied for rotation. Moment of couple. Figure illustrates the effect produced by a couple. AB is a bar which is pivoted at a point O. At the ends A and B, two equal and opposite forces, each of magnitude F, are applied. The perpendicular distance between the two forces is AB, which is equal to D, which is called the couple arm. The two forces cannot produce the translational motion as their resultant sum in any direction is zero, but each force has the turning effect on the bar in the same direction. Thus, the two forces together form a couple which rotates the bar about the point O. In figure, the two forces rotate the bar in anti-clockwise direction. Moment of force F at the end A is equal to F into OA anti-clockwise. Moment of force F at the end B is equal to F into OB anti-clockwise. Total moment of couple, that is moment of both the forces, is equal to F into OA plus F into OB, which equals F into OA plus OB, which equals F into AB, which further equals F into D anti-clockwise. Thus, moment of couple is equal to either force into perpendicular distance between the two forces or couple arm. Equilibrium of bodies. We have read that when a force acts on a body, it can produce translational motion if the body is free to move, or can produce rotational motion if the body is fixed at a point. But in certain circumstances, it is possible to apply a number of forces, two or more, such that first, the resultant of all forces is zero, so they do not change the state of rest or linear motion of the body, and second, the algebraic sum of moment of all forces about the fixed point is zero, so they do not change the rotational state of the body, then the body is said to be in equilibrium. Thus, When a number of forces acting on a body produce no change in its state of rest or of linear or rotational motion, the body is said to be in equilibrium. Kinds of equilibrium. The equilibrium is of two kinds. 1. Static equilibrium, and 2. Dynamic equilibrium. 1. Static equilibrium. When a body remains in the state of rest under the influence of several forces, the body is in static equilibrium. Examples. First, in figure, if a body lying on the tabletop is pulled by a force F to its left and by an equal force F to its right along the same line, the body does not move. What is the reason for it? The reason is that the applied forces are equal and opposite along the same line, so they balance each other. That is, there is no net horizontal force on the body. Hence, the body remains at rest, that is, in static equilibrium. Second, if a book is lying on a table, the weight of the book exerted on the table vertically downwards is balanced by the equal and opposite force of reaction exerted by the table on the book vertically upwards. Thus, the book is in static equilibrium. Third, in a beam balance, when the beam is balanced in horizontal position, the clockwise moment of force due to the object on its right pan balances the anti-clockwise moment of force due to weights on its left pan, and the beam has no rotational motion. That is, it is in static equilibrium. Dynamic equilibrium. When a body remains in the same state of motion, translational or rotational, under the influence of several forces, the body is said to be in dynamic equilibrium. Let's see some examples. First, a raindrop reaches the Earth's surface with a constant velocity. The weight of the falling drop is balanced by the sum of the buoyant force and the force due to friction or viscosity of air. Thus, the net force on the drop is zero, so it falls down with a constant velocity. Second, an aeroplane moves at a constant height when upward lift on it balances its weight downwards. Third, a stone tied at the end of a string when whirled in a circular path with a uniform speed is in dynamic equilibrium because the tension in string provides the centripetal force required for circular motion. Similarly, the motion of a planet around the sun, or the motion of a satellite around the planet, or the motion of an electron around the nucleus of an atom are in dynamic equilibrium. In each case, the force of attraction on the moving body provides the centripetal force for circular motion. Conditions for equilibrium. From the above examples, we find that the following two conditions must be satisfied for a body to be in equilibrium. 1. The resultant of all the forces acting on the body should be 0. 2. The algebraic sum of moments of all the forces acting on the body about the point of rotation should be 0. That is, the sum of the anti-clockwise moments about the axis of rotation must be equal to the sum of the clockwise moments about the same axis. Principle of moments. When several forces act on a pivoted body, they tend to rotate it about an axis passing through the pivot. The resultant moment of all the forces about the pivoted point is obtained by taking the algebraic sum of the moment of each force about that point. To find the algebraic sum, the anti-clockwise moment is taken positive, while the clockwise moment is taken negative. According to the principle of moments, if the algebraic sum of moments of all the forces acting on the body about the axis of rotation is 0, the body is in equilibrium. Thus, according to the principle of moments, in equilibrium, sum of the anti-clockwise moments is equal to sum of the clockwise moments. Let this be equation 4. A physical balance or beam balance works on the principle of moments. Verification of the principle of moments. Suspend a meter rule horizontally from a fixed support by means of a strong thread at O, as shown in figure. Now suspend two spring balances, A and B, on the meter rule on either side of the thread. Suspend some slotted weights W1 and W2 on the spring balance. The meter rule may tilt to one side. Now adjust either the slotted weights on the spring balance or the position of the spring balance on either side of thread in such a way that the meter rule again becomes horizontal. Let the weight suspended from the spring balance A on the right side of thread be W1 at a distance OA is equal to L1, while the weight suspended from the spring balance B on the left side of the thread be W2 at a distance OB is equal to L2. The weight W1 tend to turn the meter rule clockwise, while the weight W2 tend to turn the meter rule anti-clockwise. Clockwise moment of weight W1 about the point O is equal to W1 into L1. Anti-clockwise moment of weight W2 about the point O is equal to W2 into L2. In equilibrium, when the meter rule is horizontal, it is found that W1 into L1 is equal to W2 into L2. That is, clockwise moment is equal to anti-clockwise moment. This verifies the principle of moments. Center of gravity. Center of gravity. We have read in class 9th that the gravitational force between two masses is always attractive. The Earth attracts every particle towards its center by the force of gravity on the particle, which is called the weight W of the particle. A body can be considered to be made up of a large number of particles of weight W1, W2, W3, and so on. As the size of the body is quite small in comparison to the size of the Earth, the force of gravity, W, acting on these particles can be assumed to be parallel to each other as shown in figure. All these parallel forces acting in the same direction, that is vertically downwards towards the center of Earth, can be replaced by a single force W of magnitude equal to the sum of all these forces. That is, W is equal to W1 plus W2 plus W3 plus and so on, where W is total weight of the body. Now the question arises, where should the weight W act? The weight W is considered to act at a point G such that the algebraic sum of moments due to weights W1, W2 and so on of each particle about the point G is 0. The point G is called center of gravity of the body. In other words, the body can be considered as a point particle of weight W placed at its center of gravity. Thus, the center of gravity, CG, of a body is the point about which the algebraic sum of moments of weights of all the particles constituting the body is 0. The entire weight of the body can be considered to act at this point, howsoever the body is placed. Example. Note 1. The position of the center of gravity of a body of given mass depends on its shape, that is, on the distribution of mass of particles in it. It changes if the body is deformed. Example: the center of gravity of a uniform wire is at the middle of its length. But if the same wire is bent into the form of a circle, its center of gravity will then be at the center of the circle. 2. It is not necessary that the center of gravity always be within the material of the body. Example: the center of gravity of a ring or a hollow sphere lies at its center where there is no material. 3. By the concept of center of gravity, a body of weight W can be considered as a point particle of weight W at its center of gravity. Center of gravity of some regular objects. Objects and their position of center of gravity. 1. Rod. Position of center of gravity is midpoint of rod. 2. Circular disc. Geometric center. 3. Solid or hollow sphere. Geometric center of the sphere. 4. Solid or hollow cylinder. Midpoint of the axis of cylinder. 5. Solid cone. At a height h by 4 from the base on its axis, if h is equal to height of cone. 6. Hollow cone. At a height h by 3 from the base on its axis, if h is equal to height of cone. 7. Circular ring. Center of ring. 8. Triangular lamina or scalene triangle. The point of intersection of medians. 9. Parallelogram. Rectangular lamina. Square or rhombus. The position of center of gravity is the point of intersection of the diagonals. Figure shows the position of center of gravity by the point G for a circular ring, a circular disc, a triangular lamina, a rectangle, a parallelogram, a square lamina, a rod, and a cylinder. Center of gravity and the balance point. A solid body can be balanced by supporting it at its center of gravity. For example, a uniform meter rule has its center of gravity at the 50 centimeter mark. It can be balanced on a knife edge or fingertip by keeping it exactly below the 50 centimeter mark as shown in figure. It is possible because the algebraic sum of moments of the weights of all particles of rule about the knife edge or fingertip is 0. Similarly, a square thin sheet or lamina can be balanced on the tip of a nail as shown in figure. If a body is freely suspended from a point, it comes to rest, that is balances, in such a position that its center of gravity lies vertically below the point of suspension. This fact can be used to locate the position of center of gravity of an irregular lamina. Determination of center of gravity of an irregular lamina by the method of balance using a plumb line. Let A be an irregular lamina in figure for which the position of center of gravity is to be determined. Make 3 fine holes at A, B, and C near the edge of the lamina. Now suspend the given lamina along with a plumb line from the hole A using a pin or a nail clamped horizontally on a retort stand. Check that the lamina is free to oscillate on the nail about the point of suspension. When lamina has come to rest, draw a straight line AD along the plumb line. Repeat the procedure by suspending the lamina through the hole B and then through the hole C, for which we get straight lines BE and CF respectively. It is noticed that the lines AD, BE and CF intersect each other at a common point G, which is the position of center of gravity of the lamina. Note: for the stable equilibrium of a body, its center of gravity must be as low as possible. It must be above the base and near the geometric center of the body. C. Uniform circular motion. Uniform circular motion. When a particle moves with a constant speed in a circular path, its motion is said to be the uniform circular motion. In such a motion, the particle travels equal distance along the circular path in equal intervals of time, so the speed of particle is uniform, but the direction of motion of the particle changes at each point of circular path. The continuous change in the direction of motion implies that the velocity of the particle is non-uniform or variable, that is, the motion is accelerated. Direction of velocity at any instant in circular path. Figure shows a particle moving in a circular path in a horizontal plane with uniform speed v in the anti-clockwise direction. The particle travels each quarter of circle AB, BC, CD, and DA in same interval of time. Small t is equal to capital T upon 4, where capital T is the time taken by the particle in one round of the circular path. Thus, the speed of particle is constant or uniform, but the direction of motion of the particle is different at different points of the circular path. At any point, the direction of motion is along the tangent drawn at that point of the circular path. At the point A, the direction of motion of the particle is towards north. After completing quarter of circle, at the point B, the direction of motion of particle is towards west. After completing half circle, at the point C, the direction of motion of particle is towards south, and after completing 3/4 of circle, when the particle is at the point D, its direction of motion is towards east. Thus, the velocity of particle in circular motion is variable, or the circular motion is accelerated even though the speed of particle is uniform. Difference between the uniform circular motion and uniform linear motion. In uniform linear motion, the speed and velocity are constant and acceleration is zero. That is, the uniform linear motion is an unaccelerated motion, while in a uniform circular motion, the velocity is variable, although the speed is uniform, so it is an accelerated motion. Centripetal and centrifugal force. Centripetal force. We have read that a force is needed to change the direction of motion of a particle or to change the velocity of the particle, that is to produce acceleration. A particle moving in a circular path continuously changes its direction of motion at each point of its path. This change in direction of motion cannot be brought without a force. Thus, the motion in circular path is possible only under the influence of a force which is termed as the centripetal force. At each point of circular path, this force is directed towards the center of the circle as shown in figure. Thus, the direction of acceleration also changes at each point of the circular path, but its magnitude remains same, that is, the acceleration is variable or non-uniform. Hence, for a body moving in a circular path, a force is needed which acts as the centripetal force. Thus, centripetal force is the force acting on a body moving in a circular path in a direction towards the center of circular path. Examples. 1. In an atom, an electron moves around the nucleus in a circular path for which the centripetal force is obtained from the electrostatic force of attraction on the negatively charged electron by the positively charged nucleus. 2. A planet moves around the sun in a circular path for which the gravitational force of attraction on the planet by the sun provides the necessary centripetal force. 3. The moon moves around the earth in a circular path for which the gravitational force of attraction on the moon by the earth provides the centripetal force. 4. When a stone tied at the end of a string is whirled in a circular path holding its other end in the hand, the tension on the string provides the centripetal force. If this force, that is tension, is not present, the stone will not turn to move in the circular path. In all the above examples, the body moves in a circular path with a uniform speed under the influence of a centripetal force, and it is in dynamic equilibrium. Centrifugal force. A force assumed by an observer moving with the body to act on the body in direction away from the center of circular path is called the centrifugal force. Thus, centrifugal force is in a direction opposite to the direction of centripetal force. Its magnitude is the same as that of the centripetal force. But the centrifugal force is not the force of reaction of the centripetal force, because action and reaction do not act on the same body. It is not the real force, but it is a fictitious force assumed by an observer moving in circular path along with the body. To understand this force, consider the following experiment. Experiment. Figure shows a ball tied at one end of a string, the other end of which is tied at the center of a merry-go-round. Initially, when the platform of merry-go-round is stationary, the ball is seen stationary and the string is loose. As the platform starts rotating, the string becomes tight due to tension T in it. The motion of ball is observed by two persons. First, standing outside the merry-go-round on the ground at M, and second, standing on the platform of merry-go-round at A. The person standing on the ground at M, outside the merry-go-round, observes that the ball is moving in a circular path shown by dotted line, while the person standing on the merry-go-round at A observes that the ball is stationary, placed just in front of him at P. As the merry-go-round rotates, the position of person on the platform changes from A to A dash, A double dash, A triple dash, and so on, and the ball reaches at the position P dash, P double dash, P triple dash, and so on, respectively, as if it remains at rest always just in front of him. The different observations of the same motion by the two persons at M and A are explained as follows. Explanation. For the person at M, the ball moves in a circular path because the tension T in the string provides the centripetal force needed for the circular motion. The person at A observes the ball stationary. He considers the following two forces to act on the ball in order to understand his observation. First, the tension T of the string towards the center of merry-go-round, and second, the centrifugal force away from the center. The above two forces are equal and opposite, therefore the net force on the ball is zero. Hence it always remains stationary in front of him. Thus, a person on the rotating platform can explain his observation only by considering the centrifugal force. Case. If the string breaks when the ball is in position P, as shown in figure, the force of tension T in string ceases to act. Now the person at M, standing on the ground, will observe that the ball is moving in a straight line along the path PT, tangent drawn at the point P on the circular path, while the person at A standing on the merry-go-round will observe the ball at positions P dash, P double dash, P triple dash, when he will be at positions A dash, A double dash, A triple dash, etc., respectively. That is, he will observe that the ball always remains in front of him, moving radially away from him, as if a centrifugal force acts on the ball away from the center. Thus, the person in rotating frame, merry-go-round, has to assume the presence of the centrifugal force. Conclusion. The centrifugal force is not a real force. It is a fictitious force. The only force involved here is the force of tension in the string acting towards the center, that is, the centripetal force. A force which really does not exist, but is considered to describe or understand a certain motion, is called a fictitious force or virtual force.